On our previous lecture, we have talked about magnetic field, and we have learned that magnetic field may be produced by electric current, and there is an interaction between magnetic field and electric current, and this interaction is known as Ampere's force. And the interaction between moving point charge and the magnetic field is known as Lorentz force. Is known as Lorentz force. And what is interesting? It is interesting the question if magnetic field may be produced by electric current. Can be opposed situation when magnetic field produces electric current, and the answer is yes. The answer is yes, and because magnetic field may also produce electric current. So let's have a look at a closed circuit. Let's have a look at closed circuit, and let's define magnetic flux. Let's define magnetic flux through this closed circuit. So magnetic flux. Magnetic flux. Magnetic flux. Magnetic flux. It is a surface integral. Magnetic flux FB. FB is a surface integral. Surface integral. Some circuit SL. B magnetic induction, and DS. So this is magnetic flux. This is a magnetic flux, and British scientist Maxwell-Faraday discovered in the 19th century that change in magnetic flux through closed circuit produces electric current in this circuit, and this electric current is known as induction. Is known as the induction current, and this production of induction current is known as electromagnetic induction. And the next question is how to define the direction. How to define the direction of inductive current. How to define the direction of inductive current. And the answer on these questions is given by Lenz rule. Let's write this Lenz rule. Lenz rule. Lenz rule. Lenz rule. According to this rule, the current inductant in a circuit, so the current inducted in a circuit, due to a change in a magnetic field, due to a change in a magnetic field, due to a change in the magnetic field, is directed to oppose the change in flux, to oppose the change in flux, directed to oppose the change in flux, and to exert mechanical force which opposes the motion, and to exert a mechanical force, which opposes the motion, which opposes the motion, which opposes the motion, So Lenz rule. The current inducted in the circuit due to a change in a magnetic field is directed to oppose the change in flux and to exert a mechanical force which opposes the motion. Maybe it is quite difficult to understand for the first time. In similar way, it can be said as that inducted current is always opposed to factor that caused this current. So let's have a look at an example. Let's have a look at an example of a closed circuit. So if we have some closed circuit, for example this closed circuit, and there is a magnetic field through this circuit. Magnetic field B, and let's have a look at the situation when absolute value of this magnetic field decreases. Magnetic field is decreasing. In this case, magnetic flux will change. Magnetic flux will change, and it means that inductive current will occur. But there are two directions. There may be two directions, this and this, and which direction will be correct? Which direction should we choose in this situation? For inducted current? And we may use Lenz rule. We may use Lenz rule. According to this rule, inducted current must compensate decreasing in magnetic field. And it means that we should choose this direction. This direction. Why? Because this direction, this current will produce magnetic field like this, and this magnetic field will compensate decreasing in external magnetic field. Okay, do you have any questions about this? No questions. Okay, there are no questions. So the next thing to learn is how to connect current, inducted current and change in magnetic flux. How to connect, because we already know that change in magnetic flux will produce inductive current. But it is necessary to know the connection between these values, between magnetic flux and inductive current. To understand this connection, let's have a look at next circuit. Let's have a look at conductive frame. Some conductive frame that looks like this. Some conductive frame. Nice conductive frame, and this frame has wire, or thin rod, that is also conductive. It may conduct electric current, and it may slip. It may move along. This frame. It may move from left to the right, and from right to the left. And let's have a look at the situation when this frame is in an external magnetic field. When it is an external magnetic field, B that is perpendicular to the frame. External magnetic field that is perpendicular to the frame. And this distance is equal. This distance is equal to L. This distance is equal to L. And the velocity of this rod is v. This is v. The velocity of this rod is v. This is v. Okay, and why inductive current? Why does inductive current occur in this situation? It will occur because magnetic flux will change, and the magnetic flux will change because of increase of area of the frame. This area is area of closed circuit, and it will increase. It will increase as a result of motion of the rod. So the area will increase, and it means that magnetic flux in this situation will change. So inductive current will be produced in this situation. So the next question is how to define the direction of this inductive current. How to define the direction? There may be two directions, and we should choose one of them. Electric current in inductive current in the rod may have two directions, this and this. So which direction should we choose? We should do this according to the Lenz rule. According to this rule, inductive current must be opposed to the some factors that caused it. It must be oppose the motion of the rod. So it must produce a force. That is directed to the right. So inductive current must produce force and it will be amperes force. And this amperes force must be directed opposed to the velocity, according to the Lenz rule. And this allows us to define the direction of induction current. So how to do this? We can use left hand rule. According to this rule, magnetic induction vector B must be directed to the palm. And so in this case, we have to put our left hand rule in this way. So vector B is directed to the palm. Vector FA has the same direction as the thumb, and the other fingers will show us the direction of inductive current. So the direction of inductive current will be this. Okay. Do you have any questions about this situation? So the direction of inductive current in this situation will be anti-clockwise. Anti-clockwise. Okay, and now we know this direction, and we may try to we may try to we may try to calculate. We may try to calculate Lorentz force. Lorentz force that is a result of this velocity. Let's try to calculate Lorentz force that is a result of this velocity. So the rod moves with velocity v, and charges inside the rod will move with it, with the same velocity. So it means that some force F, it will be Lorentz force F, for example, FL. Lorentz force F that is caused by velocity v. So this Lorentz force may be calculated from here, and FL will be equal to charge Q. Charge Q is a charge inside the rod. Charge inside the rod, and multiplied by cross product V and B. So let's find the absolute value. Let's find the absolute value. The absolute value of this absolute value of this force. So FL Lorentz force, absolute value of Lorentz force is equal to modulus of vector FL, and it will be equal to Q V B QVB multiplied by sinus, and here inside in argument of sinus will be angle between vector V and vector B. So if we have vector V velocity in on our screen, and vector B magnetic induction is perpendicular to the screen, it means that the angle between vectors V and B will be 90 degrees. 90 degrees. So it is equal to Q V B. It is equal to Q V B. It is equal to Q V B. And the next step, what we need is to calculate work of this Lorentz force, because this work will be the main cause of inductive current in this situation. So we can remember from mechanics. That this work is equal to the integral of FL dl, fl dl, and the length of the path should be from 0 to L. L is length of the rod. And as we know, the element dl is, of course, has the same direction as fl. So we can rewrite this integral without vectors. Because fl, vector fl has in this situation has the same direction as vector dl. Vector dl. Vector dl is the element of this rod. Infinitely small element of this rod. This is infinitely small element of this rod. So according to this, we have that it will be f l d l. The same integral, but without vectors. Without vectors, that is much more simpler than it was before. Much more simpler than it was before. And we can make substitution. We can make substitution here. It will be the integral from 0 to L. From 0 to L. Here we have Q, V, B, Q, V, B, dl, dl. And Q and V and B doesn't depend on element of the rod dl. So it means that these values may be written outside of the integral. So we will have in this situation we'll have QVB integral from 0 to L, dl, and it will be, of course, it will be equal to QVB multiplied by L. Okay, do you have any questions? No questions. Okay, this is the work of the Lorentz force. Work of the Lorentz force. So okay, let's clean the screen and remove some things that we don't need anymore. And let's continue. So we have calculated this work. Work of Lorentz force. Okay, and what about magnetic flux in this situation? What about magnetic flux? We can say that there will be increase. There will be increase of area of the circuit, and this increase may be shown in the next way. So if previous position of the rod was here, was here in dashed line, and we can sign this increase like in this way, and if we have so I will roll this in. I will show this in this way. Oh, it's better to. Mhm. I cannot move this line. Okay. Uh, okay. Yes, I have managed to do this. Uh, okay, so and this distance will be equal to dx. The change of position of the rod will be some dx. It will be dx. dx. It will be dx, and of course, it will be equal to velocity multiplied by time. It will be equal to velocity multiplied by time. Multiplied by time. Okay, and what about area? What about area? This area has a rectangular form, and according to the picture, area ds will be equal to dx will be equal to L multiplied by dx. Area of rectangle. Of course, is equal to product of its sides. Product of its sides. And the last question is how to define the direction of this increase ds. How to define the direction? It can be done. With right hand rule. According to the direction. Of inductive current. Uh, so if we for example, if we rotate screw according to the direction of induction current, if we rotate a screw uh, uh, anti-clockwise, it will move from the screen to us. So vector ds will be directed from the screen to us. Vector ds is from the screen to us. Okay, and how to find change of magnetic flux in this situation? It will be d phi b is equal is equal to B magnetic induction ds vector. And as we can see, according to the picture, vector ds and vector b have opposed directions. They have opposed direction. In other words, they are anti-parallel. We have two anti-parallel vectors. Anti-parallel vectors, so we have vectors with opposed directions. And it can be written in this way, ds. Two vectors has opposed direction. And it means that we can write this scalar product. It will be B ds multiplied by cosine, and for vectors with opposed direction, the angle between them will be 180 degrees. The angle will be 180 degrees. 180 degrees. And cosine of 180 degrees is -1. So it will be minus B ds. Minus B ds. Okay, and let's return to our picture. As we have found that increase in area ds is equal to L multiplied by increase of coordinate of the rod. So it will be L dx. L dx. So we can write minus B L dx. dx. Okay, let's return to our picture again, where we have found that increase in coordinate dx is equal to v, velocity v, multiplied by differential of time dt, or increase of time dt. So it will be minus b L v dt. Okay, and do you have any questions about this? Do you have any questions about this? No questions. No questions. Okay, if there are no questions, if there are no questions, I'll clean some things that we don't need anymore from the screen, and I will leave just final result. Just final result that increase of magnetic flux is equal to this value. Okay, so we have obtained a system of two equations, and what to do with them? What to do with them? We can make some algebraic transformation of it. We can make some algebraic transformation, and from this we will find that it will be B L. From the first equation, we have BLV is equal to A work divided by electric charge. But work divided by electric charge, as we can remember from one of our previous lessons. This relation is equal to electromotive force. It is equal to electromotive force, and in this case, this is electromotive force of induction. Electromotive force of induction, and this is the main cause of inductive current. Okay, and from the second equation, we have BLV is equal to minus DFB minus DFB divided by dt. Sorry, I have blackout. We have blackout in Kiev, so it may be some problems with the internet connection. But I hope we will avoid this. Uh, I hope we will avoid this situation. Okay, so let's continue. It seems that everything is okay. So, and minus df b by dt by dt by dt b by dt. So first derivative. Okay, and if the left sides are equal, BLV, the right sides of equations must be also equal. To. They must be equal to. So from here we can obtain this equation minus d phi b divided by dt. Okay, do you have any questions? Do you have any questions? No questions. No questions? So we have obtained so-called Faraday's law of induction. Faraday's law of induction, or simple Faraday's law. Faraday's law of induction. We have obtained this law for partial case, but according to the experiment, during the experiments, it was proven that this law is universal, and this law is true in all cases. This law is true for all cases. Not only for this. So I may remove this. And what thing is necessary? What's the next thing that is necessary to say? What is the next thing? The next thing is uh, very often uh, closed circuits uh, are connected in series. Are connected in series to increase in order to increase electromagnetic induction. And if we connect many circuits in series, uh, electromagnetic inductions in them will be added according to properties of connection in series. So we'll have electromotive force of induction is equal to electromotive force in first circuit plus electromotive force in second circuit plus and it will be equal to minus d and dt d and dt the sum of fb, and this value the sum of magnetic flux is known as flux linkage. This is known as flux linkage. This is a flux linkage, and it can be written as Greek letter psi, and it is equal to sum of fb, This is a flux linkage. This is a flux linkage. Okay, and from here and from here, we'll have that electromotive force of induction. Electromotive force of induction is equal to minus d psi d psi dt d psi and dt. Okay, what questions do you have about this formula? No questions. No questions. Okay, if there are no questions, let's write this law in red frame. Let's write this law in red frame. So it is Faraday's law of induction. Faraday's law of induction. Faraday's law of induction. And this is Faraday's law of induction. Faraday's law of induction. Okay, which questions do you have? No questions. Okay, if there are no questions, If there are no questions, let's remember another definition. Let's remember another definition of electromotive force. It can be defined. It can be defined as integral, linear integral along the closed circuit, circuit L of integral where E is En, for example. This is non-electrostatic field intensity. Non-electrostatic field intensity. It is signed with this lower index n multiplied by dl, and this may be written as integral along the closed circuit L. Here non-electrostatic field intensity dl, and we can write plus integral along the closed circuit of electrostatic field intensity. Why can we do this? Because we know from electrostatics that electrostatic field is always potential field. It is always potential field, and it means that this integral is equal to 0. And because this integral is equal to 0, we can write this equation. Okay, so let's unite these two integrals. Along the circuit L, E non-electrostatic plus electrostatic part of electric field. And the sum of these two vectors is known as electric field intensity. So this is electric field intensity. This is electric field intensity. This electric field intensity. Okay, E dl. Okay, do you have any questions about this? No questions. Okay, if there are no questions, I will clean some things from the screen. And what to do with this? What can we do with this derivative? If we have only one circuit, the flux linkage will be equal to magnetic flux in this circuit. And in this situation, we can write that minus deep C by dt. In case of only one circuit, in case of only one circuit, it will be minus d and dt, d and dt, surface integral SL b ds Okay, and this will be equal to minus surface integral SL and dB ds dt. I have changed the derivative into partial derivative because magnetic field changes only with time, but not with coordinates. And ds and ds. So what do we have? What do we have from these equations? We can substitute them into Faraday's law of induction, and from here we will get integral form of Maxwell-Faraday equation. Maxwell-Faraday equation. So it is equal to this. It's equal to this. Okay, what questions do you have? No questions. Okay, if there are no questions, let's write the final result in red frame. Let's write the final result in red frame. So it is Maxwell-Faraday equation in integral form. Maxwell-Faraday equation in integral form. In integral form. Maxwell-Faraday equation in integral form. And if we use Stokes theorem, we will remember that this linear integral, according to the Stokes theorem, EDL, and this is equal to the surface integral SL according to the Stokes theorem. And here we have curl E Rho E ds. Rho E ds. Okay, and from here and here, from here and here, we have Maxwell-Faraday equation. We have Maxwell-Faraday equation. In differential form. In differential form. In differential form. Maxwell-Faraday's equation in differential form. So let's write this. So it is it derives from here and from here. Minus dB and dt. dB and dt. Minus dB and dt. Okay, which questions? What questions do you have about this? No questions. No questions. Okay, if there are no questions, if there are no questions, let's have a look at another property of electromagnetic induction that is known as self-induction. What is this? Electric current is in some circuit. Electric current in circuit may produce or will produce a magnetic field around this conductor and around circuit, and it means that electric current in circuit will produce magnetic flux through this circuit. So and this is known as self-induction. This is known as self-induction. This is known as self-induction. So let's try to understand. Let's try to understand, or let's try to define flux linkage in this situation. As we know, in case of as we know that magnetic field around the conductor with electric current may be defined with a Biot-Savart law, and according to this law, it is equal to mu 0 divided by 4p electric current dl, element of a conductor with current, multiplied by vector r and divided by absolute value of r to the power of 3. And what does it mean? It means that magnetic field induction is proportional to the current E. And this means that magnetic flux will also be proportional to the current E, because it is proportional to vector B. And of course, flux linkage is proportional to magnetic flux, and it means that flux linkage is proportional to the current E. And this fact can be written with simple formula that flux linkage is equal to L multiplied by electric current. And where the coefficient L is a physical value that is known as inductance. So L is inductance. L is inductance. L is inductance. L is inductance. Okay, what questions do you have about this? No questions. No questions. And it is necessary to notice that we are learning only simple case when inductance L is a constant and doesn't depend on electric current E. But in general case it isn't true. In general case, inductance may depend on electric current. So the dependence will be more difficult. Will be more difficult than this. Okay, but what will we have in this simple case? Let's make substitution. So let's use this in Faraday's law of induction. From here we will have that electromotive force of self-induction, electromotive force of self-induction is equal to minus L derivative of electric current. Derivative of electric current. Okay, what questions do you have about this? No questions. No questions. So electromotive force or EMF of self-induction. Electromotive force or EMF of self-induction. Electromotive force of self-induction. Okay, and let's try to find inductance for simple system. Let's try to find inductance of simple system. That is known as solenoid or induction coil. What is this? What is this? This is a wire that has a form of the spring, that looks like a spring with many uh, coils, spring with many coils, and the current in it is here. A solenoid of or inductor. Maybe the best name is inductor, and it will be proven. We will prove tomorrow that magnetic field inside inside this element is homogeneous. Is homogeneous. Magnetic field is homogeneous. Is homogeneous, and and magnetic induction, absolute value of magnetic induction is equal to mu 0 n e, where n is a number of coils per length unit. Number of coils per length unit. For example, per meter or per centimeter or kilometer. And what about inductance? Inductance of inductor. What will we have? It is necessary to find flux linkage, and it will be number of coils multiplied by magnetic flux in one coil. And this big letter N is equal to N multiplied by L phi B. But we know that this phi B magnetic flux is equal to this integral, but in this case the field is homogeneous, so we can just write that it will be n l b s, and it will be equal to mu 0 n to the power of 2 n to the power of 2. What will be here? N to the power of 2 I s l and area of a coil multiplied by the length of all coils will be equal to the volume inside these coils. So we'll have mu 0 n to the power of 2 I v. And according to this formula, all these values will be equal to L E. And from this equation, we will have that inductance of inductor will be equal to mu 0 n to the power of 2 n to the power of 2 s l, and this will be mu 0 n to the power of 2 v. This is inductance of an inductor. Okay, what questions do you have? No questions. Okay, there are no questions. I'll just write a final result. And I hope tomorrow we'll prove this formula. This. And now we can write that inductor has magnetic field inside it, and that can be calculated with this formula, and inductance of inductor is can be calculated with this formula. Okay, do you have any questions about this? Okay, so if there are no questions, I think we can finish. Today's lesson on this, and I hope to meet you tomorrow.